Class 11th, Subject Physics, 7th Chapter, Thermal Properties of Matter. Thermal Properties of Matter. From this chapter, let us see the thermal expansion, that is thermal expansion of solids. Now if we consider the thermal expansion of the solids, there are three different expansion of the solid, namely first one, that is linear expansion, second areal expansion, and third volume expansion. So when heat energy is supplied to any solid, then depending upon the shape of that solid, there may be change in its length or change in its area or change in its volume, and therefore there are three types of expansion, that is linear expansion, areal expansion, and volume expansion. Let us see these expansions one by one. First one, that is linear expansion. If there is increase in length of the solid due to the thermal energy, that is heat energy supplied to it, then the expansion of the solid is said to be linear expansion. That is, in case of linear expansion, due to the heat supplied to that solid, there will be increase in its length. So in order to explain this linear expansion, let us consider a rod of length L. When there is change in temperature, that is delta T supplied to this rod, at that time there will be increase in its length, that is equal to delta L. That is, the original length of this rod is L, and when there is small change in temperature delta T, at that time there will be increase in its length, that is equal to delta L. And therefore experimentally it is observed that the fractional change, that is delta L upon L, in the length of the solid, the fractional change delta L upon L, that is change in length per unit original length, is directly proportional to rise in temperature or increase in temperature delta T, and therefore delta L upon L will be proportional to delta T. Or by removing the proportionality sign, we can write delta L upon L equal to alpha delta T. Alpha delta T, where this alpha is the constant of proportionality, which is called as the coefficient of linear expansion of that solid. Coefficient of linear expansion of that solid, and therefore we can write alpha equal to delta L upon L into delta T. Delta L upon L into delta T. Now let L0 be the length of that rod at T0 degrees Celsius temperature. So L0 is the length of the rod at T0 degrees Celsius temperature. Similarly, LT will represent the length of the rod at T degrees Celsius temperature. LT is the length of the rod at T degrees Celsius temperature. Therefore, increase in length of the solid will be equal to increase in length of that rod will be equal to LT minus L0. LT minus L0, and rise in temperature of that rod will be equal to T minus T0 degrees Celsius. T minus T0 degree Celsius. Therefore, the coefficient of linear expansion alpha will be written as alpha equal to delta L upon L into delta T will be equal to LT minus L0, because this delta L, that is change in length, is LT minus L0 upon L0 into T minus T0. Now, if from this relation, if L0 equal to 1, if this L0 equal to 1, that is unity, and temperature difference T minus T0 is also 1, that is unity, then from this relation, as alpha equal to LT minus L0 upon L0 into T minus T0, in this case L0 is equal to 1, T minus T0 equal to 1, and therefore alpha will be equal to LT minus L0, and therefore we will get alpha is equal to LT minus L0. And so from this we can define the coefficient of linear expansion alpha. So the coefficient of linear expansion alpha is defined as the increase in length of the solid, per unit its original length at 0 degrees Celsius temperature, per unit its original length at 0 degrees Celsius temperature per degree rise in temperature, So the coefficient of linear expansion of the solid is defined as increase in length of the solid per unit its original length at 0 degrees Celsius temperature per degree rise in temperature. Now instead of that, if we consider L1 and L2 are the lengths of the rod at T1 degrees Celsius and T2 degrees Celsius temperature respectively. So at temperature T1 length will be equal to L1, and at temperature T2 length will be equal to L2. Then coefficient of linear expansion alpha will be given as L2 minus L1 upon L1 into T2 minus T1. Alpha is equal to L2 minus L1 upon L1 into T2 minus T1. Now let us see the second type of expansion, that is areal expansion. If there is change in area of any solid due to the thermal energy supplied to it, then the expansion is areal expansion. That is, in case of areal expansion, there will be change in area of that solid due to the heat energy supplied to it. And therefore, in order to explain this areal expansion, let us consider a rectangular plate having its area equal to A. Then when heat energy is supplied to it, at that time a small change in temperature will be there. Due to that change in temperature, the area of this plate will increase by factor delta A. It is dA or delta A. And therefore, if there is increase in area of the plate due to small change in temperature delta T, then experimentally it is observed that the fractional change delta A upon A in area, fractional change in area, that is delta A upon A, will be proportional to delta T. That is, fractional change in area of that plate is directly proportional to change in temperature, that is delta T. And therefore we can write by removing this proportionality sign, delta A upon A equal to beta into delta T. Delta A upon A equal to beta into delta T, where beta is the constant of proportionality, which is called as the coefficient of areal expansion of the solid. The coefficient of areal expansion of the solid, and it will be given as delta A upon A into delta T. Delta A upon A into delta T. Now suppose A0 represents area of that plate at T0 degrees Celsius temperature. If A0 is the area of that plate at T0 degrees Celsius temperature, and AT represents area of the plate at T degree Celsius temperature. AT is area of the plate at T degree Celsius temperature. Then increase in area of that plate will be equal to AT minus A0. And rise in temperature will be T minus T0 degree Celsius. And therefore the coefficient of areal expansion beta will be equal to delta A upon A into delta T. It will be written as AT minus A0 upon A0 into T minus T0. at minus a0 upon a0 into t minus t0. Now from this relation, if a0 equal to 1, that is unity, and t minus t0 is also 1, then beta will be equal to at minus a0. Beta will be equal to at minus a0, that is a0 is 1, t minus t0 is 1, and therefore beta will be equal to at minus a0. Now from this we can define the coefficient of areal expansion, and therefore coefficient of areal expansion of the solid is defined as increase in area of the solid, increase in area of the solid per unit its original area at 0 degree Celsius temperature per degree rise in temperature, per degree rise in temperature. So coefficient of areal expansion of the solid is defined as increase in area of the solid per unit its original area at 0 degree Celsius temperature per degree rise in temperature. Now instead of that, if you consider A1 and A2 are the areas of that plate at T1 degree Celsius and T2 degree Celsius temperatures. So at T1 degree Celsius temperature, area is A1, and at T2 degree Celsius temperature, area is A2. Then in this case, beta will be given as, then beta is equal to A2 minus A1 upon A1 into T2 minus T1. A2 minus A1 upon A1 into T2 minus T1. So this will be regarding areal expansion. Now let us consider third expansion, that is volume expansion of the solid. Volume expansion. If there is change in volume of the solid due to the thermal energy or heat energy supplied to it, then volume expansion will be defined. That is, in case of volume expansion, due to the heat supplied to the solid, there will be change in volume of that solid. And therefore, in order to explain this volume expansion, let us consider a cube whose volume is equal to phi. And then when due to heating there is small change in temperature delta T, at that time its volume will change. Its volume will change by factor delta phi. And therefore again fractional increase or fractional change in volume, that is delta V upon phi, will be proportional to change in temperature, that is delta T. So fractional change in volume, that is delta V upon phi, will be proportional to delta T, or removing the proportionality sign, we can write delta V upon phi equal to gamma delta T. Gamma delta T, where this gamma is the constant of proportionality, which is called as coefficient of volume expansion. Coefficient of volume expansion, which is given as gamma equal to delta V upon phi into delta T. Delta V upon phi into delta T. Now suppose phi 0 represents the volume of that cube at T0 degree Celsius temperature. If phi 0 is volume of the cube at T0 degree Celsius temperature, and phi T represents the volume of cube at T degree Celsius temperature. Phi T represents volume of the cube at T degree Celsius temperature. Then increase in volume of that cube, increase in volume of the cube will be equal to Vt minus phi 0. Vt minus phi 0, and rise in temperature will be again T minus T0 degree Celsius. T minus T0 degree Celsius. Therefore, the coefficient of volume expansion gamma will be equal to delta V upon phi into delta T. Delta V upon phi into delta T will be written as Vt minus phi 0 upon phi 0 into T minus T0. Vt minus phi 0 upon phi 0 into T minus T0. Now from this expression, if phi 0 equal to 1, that is unity, and T minus T0 equal to 1, that is unity, then gamma will be equal to Vt minus Phi0, gamma equal to Vt minus Phi0. So from this relation, if Phi0 equal to 1, T minus T0 equal to 1, then this gamma will be equal to Vt minus Phi0. And therefore, from this relation, we can define coefficient of volume expansion. So coefficient of volume expansion of the solid is defined as the increase in volume of the solid per unit its original volume at 0 degree Celsius temperature per degree rise in temperature. Coefficient of volume expansion of the solid is defined as increase in volume of the solid per unit its original volume at 0 degree Celsius temperature per degree rise in temperature. Now, if Phi1 and Phi2 represents, these are the volumes of the cube at T1 degree Celsius and T2 degree Celsius temperatures respectively. That is, at temperature T1, volume is Phi1, and at temperature T2, volume is equal to Phi2. Then we can write gamma is equal to Phi2 minus Phi1 upon Phi1 into T2 minus T1. Phi2 minus Phi1 upon Phi1 into T2 minus T1. So this will be regarding the expansion of the solid. So all the coefficients, that is alpha, beta and gamma, that is coefficient of linear expansion, coefficient of areal expansion and coefficient of volume expansion, all these are having same SI unit, that is per degree Celsius. Per degree Celsius. So for alpha, beta and gamma, SI unit is per degree Celsius.